So let's derive this out. We just looked at the formula. Let's derive it out. So the basic idea is we are looking at exerting any force at center of mass that will result in entire object accelerating the same. So the force which accelerates the particle individually should have the same effect. So based on this basic idea, we're looking at it. So I'll explain this. The derivation overview is to get the expression for total forces acting on the system and equate it to the force at center of mass, which would create the same acceleration. So we're talking about the word same acceleration, inter-object accelerating the same. So we are looking at this. So we're talking about force, right? I hope you guys are getting a bit of hint about what direction we are going. Now, let's take up again our x and y coordinates. And again, we are taking up 1 and 2. Okay, so let me make this the bigger one now. And this is the chotu one. Then we have the position vector. And then we have a line connecting them. So somewhere along this, we have our center of gravity, center of mass. Okay, so let's start with talking about the position vector, say R2. This is R1. This is center of mass. And this is our x and y. Origin, particle 2 with mass 2. This is particle 1 with mass 1. Right? So this is the funda. Now, let there be some external force acting on it. So let there be some external force acting on each. So we have two external force acting on each. Now, because of this, there is a velocity and acceleration. So the velocity and acceleration of the two particles, of course, because of the external force, is given by dr by dt, and we have v2, which is dr2 by dt, right? So how fast this is changing, that will give us our v1, and how fast r2 is changing, that will give us v2. Is it not? So again, this goes back to your basics of vector. Of course, your a1 will be the second derivative of, or the derivative of this actually, technically. So if I take the derivative of this expression with respect to time again, we'll end up with this. So all of this is with respect to your position vectors. Now, this being the case, our total force on, say, particle 1 will be how much? We know the acceleration, so force will be, yes, F1 is equal to your force on the by the external force plus also the force from F12 as well. That is your internal force. Okay. Total force that acts on the object is external force, and also if there is any internal force. So this is to do with your internal force. And for particle 2, it would be F2. It would be a vector addition of the external force and the internal force. F2, 1. I know I'm not showing that forces over here, but it's there. Right? Next, I'm going to substitute F21 as minus F12, right? This is your Newton's third law. So therefore, F2 can also be written as F2 external minus F12. Okay, now let's look into applying Newton's second law. So we have all the required expressions, right? So these are the net force. F1 and F2 are net force. These are the causes, and we know the acceleration. So therefore, when we apply it, so on say particle 1, it will be, again I'll go with particle 1 and 2. So on P1, it would be M1 A1 will be equal to F1 external plus F12, right? And particle 2, we're looking at M2 A2. This will be F2 external minus F12. Okay. So now if I add the above two equations, what will happen? Adding above equations. So we have M1 A1 plus M2 A2 is equal to F1 external plus F2 external, right? And these two will cancel each other. Now this I can call it as M1 A1 plus M2 A2. This is F external. That is I'm calling, actually let me do this. So instead of two forces, I'll combine them. So I'll let F external be the resultant force of F1 and F2 external. So this is nothing but your total external force. Then this happens, right? We'll call this as say equation 1. So we're going to make use of it. So we have to go back to the definition now. So we have to make use of this very idea. See, center of mass and all of this idea. Exerting any force at center of mass will result in entire objects accelerating the same. So instead of individual acceleration or individual forces acting on these two particles, I replace that with a single force. Now, if this force acts on the center of the particle, center of mass, it will result in the same acceleration. Okay, so let me start off by talking about this. Let's represent the total mass M1 plus M2 as M. Then we'll assume, let's assume F external acting on M, producing an acceleration of AC, right? Again, we are going back to I told you, everything goes back to the definition. So as per, again, Newton's second law, we know that F external will be equal to M times of A center of mass, acceleration produced at the center of mass. So we are calling, let's call this as, say, 2. Now, from 1 and 2, what can you tell? So from 1 and 2, what do we have? We have M acceleration over here. Then we have M1, A1 plus M2, A2. Right? Then I'm going to expand this. So this is double derivative of center of mass. Right? And this is again double derivative of your R1 plus, I'll write it here itself, M2 double derivative of this. Again, I'm just substituting things back. So we know the algebra of derivative. So I can rewrite this as, again, a bit of math is what I'm using. I'm skipping few steps. I hope you guys understand this. So this goes back to your fundamentals. If you're not understanding this, this is to do with your algebra of limits and derivatives. If you guys see that, you'll get to understand this. And on the LHS, we have double derivative of MRCM. So when we compare, so on comparing, what do we end up with? Derivative of a quantity is equal to derivative of that quantity, some other expression. So if the derivatives are the same, then we have M times of RCM should be equal to M1 R1 plus M2 R2. If I transpose this M over here, this entire thing divided with capital M. And this is where your center of mass is. Again, the idea of center of mass is what we are taking and deriving this. So let me recap everything. So this will make sense now. See, center of mass creates that effect, as if instead of applying force everywhere and creating a particular motion and acceleration, right? Instead of that, I can just apply the same amount of net force at center of mass and make the object move with the same, in the same manner, basically. So that's the whole idea. So basically, applying the force at this 2 point is same as applying a force of, F external over here. That's the whole idea. So all I did was writing the expression for forces. That's all. Nothing else I've done. If you look at it, all I did was write expression for, where is it? This, no, not that. Here, not that. Yeah, this only actually. Or more technically this. So F external is equal to F1 external plus F2 external. Basically this. Everything has to do with this very definition. This very line, if you understand, you're pretty much done. All I did was writing expression for this. If you look at it carefully, it's just that, nothing else. And bit of rearrangement, a bit of math, and you got the answer. Okay, so again, all this has to do with the definition of center of mass itself. Okay, and you got to see that with our experiments also. So if I happen to hit, end of each of the parts of the object with certain force and create certain, behavior, certain behavior with motion, I can get the same kind of acceleration, same kind of motion by hitting the object at the center of mass. So with that basic definition, we have derived this, as simple as that. So get the expression for the total forces acting on the system and equate it to the force at center of mass, which would create the same acceleration. That's all we did, nothing else. Okay. So now pause, have a look, wind it up.